A planet made of carbon, a sky filled with soot, and deep inside, diamonds forming under crushing pressure. That already sounds unreal, but what shocked scientists even more was where this world was found. It's not orbiting a normal star. It circles the burned-out core of a dead one, a pulsar, blasting radiation through space like a cosmic lighthouse. When NASA's James Webb Space Telescope turned its gaze toward this system, researchers expected to see the usual atmospheric fingerprints: water, methane, maybe carbon dioxide. Instead, the data revealed something no one had ever seen before: a planet dominated by pure molecular carbon. Even the scientists analyzing the signals reportedly stared at the screen thinking, "What is this?" And the deeper they looked, the stranger it became. When the first detailed spectra came back from the James Webb Space Telescope, the team studying PSR J2322-2650b expected something routine. After all, astronomers have now analyzed the atmospheres of dozens of hot, Jupiter-like worlds. There's a pattern. You look for water vapor, you search for methane, you check for carbon dioxide. These molecules leave clear fingerprints in infrared light, and Webb is designed to see them with stunning precision. The assumption was simple. This would be another extreme gas giant, but still recognizable. But as the data sharpened and the full spectrum came into view, those familiar fingerprints were missing. Completely missing. No water, no methane, no carbon dioxide. Instead, the signals were dominated by something far stranger: molecular carbon, specifically C2 and C3. That's not just unusual, it's almost unheard of. At the temperatures measured on this world, ranging from roughly 1,200 degrees Fahrenheit on the cooler side to nearly 3,700 degrees on the hotter regions, carbon should be binding itself to oxygen or hydrogen almost immediately. In normal planetary atmospheres, free carbon doesn't just float around. It reacts. It forms stable molecules. That's basic chemistry. So seeing strong signatures of pure molecular carbon suggested something extreme. There may be almost no oxygen or nitrogen present at all. Out of the roughly 6,000 confirmed exoplanets discovered so far, not a single one has shown an atmosphere like this. Not even close. Researchers reviewing the data reportedly stared at the screen in disbelief. One of them later admitted their first reaction was essentially, "What the heck is this?" Because this wasn't a small anomaly. It wasn't a subtle variation. It was an atmosphere that seemed to break the rules. And if the chemistry alone wasn't strange enough, the source of illumination, the object this planet orbits, would make the mystery even deeper. In most so-called black widow systems, the story is brutal and predictable. A rapidly spinning pulsar locks onto a nearby companion star and begins draining it, blasting it with radiation and particle winds until the smaller object is slowly stripped away. Over time, that companion can be reduced to almost nothing. But here's the twist. In this system, the object being battered isn't a star. It's officially classified as a planet. PSR J2322-2650b sits just about 1 million miles from its pulsar host, PSR J2322-2650, locked in an orbit so tight that an entire year flashes by in only 7.8 hours. That proximity comes at a cost. The pulsar's gravity is so overwhelming that the planet is being stretched out of shape, pulled into a distorted, almost lemon-like form. Imagine tides on Earth. Now multiply that force to cosmic extremes. The side facing the pulsar is constantly scorched, while the far side cools dramatically, creating temperature swings that would tear apart most known atmospheres. And all the while, high-energy radiation bombards the planet without mercy. Over time, systems like this are expected to end with the pulsar completely consuming its companion. That's why they're compared to black widow spiders. But this case doesn't follow the usual script. The companion hasn't vanished. It hasn't been reduced to debris. Instead, it remains a Jupiter-mass world with a chemical makeup unlike anything we've seen. And that raises an uncomfortable question. If it didn't form like a normal planet, and it isn't simply the leftover core of a destroyed star, then what exactly are we looking at? Now here's where it turns from strange to almost unreal. The atmosphere of PSR J2322-2650b isn't just carbon heavy. It may actually produce diamonds. Temperatures across the planet swing from roughly 1,200 degrees Fahrenheit on the cooler night side to nearly 3,700 degrees on the day side facing the pulsar. In conditions like that, carbon doesn't behave gently. It can form thick, sooty clouds in the upper atmosphere, darkening the sky with fine black particles. But deeper down, under crushing pressure and extreme heat, that carbon may begin to crystallize. Some researchers have proposed that inside this world, carbon and oxygen mixtures could separate as the planet cools internally. In that process, pure carbon crystals might form and rise upward, mixing into the helium-rich layers above. If that idea is correct, and it's still a working hypothesis, then parts of this planet's interior could resemble an enormous, naturally forming diamond factory. Not polished gemstones, of course, but massive crystalline structures forged by pressure and time. It sounds almost like science fiction. A scorched world orbiting a dead star, wrapped in soot clouds, possibly raining carbon crystals. But even that dramatic picture doesn't solve the core mystery. Because for carbon to dominate like this, something critical has to be missing. And that missing ingredient may be the biggest clue of all. Here's the problem that's keeping scientists up at night. This planet shouldn't be chemically possible. According to everything we know about planetary formation, carbon doesn't just end up alone. In normal protoplanetary disks, carbon eagerly bonds with oxygen, hydrogen, or nitrogen. It forms stable molecules. It spreads out. It doesn't dominate an atmosphere by itself. And yet, on PSR J2322-2650b, molecular carbon appears to be the main ingredient. That immediately rules out the simplest explanation, that it formed like a typical gas giant. But the alternative isn't much better. In most Black Widow systems, the pulsar strips material from a companion star, gradually peeling it apart. Some have suggested this planet could be the leftover core of a once larger star that was eroded down over time. The issue? Stellar nuclear processes don't naturally produce a body made almost entirely of carbon, without significant oxygen mixed in. Physics just doesn't cooperate. So researchers are stuck in a strange position. If it didn't form like a planet, and it didn't form like a stripped-down star, then what pathway created something this carbon-enriched? Where did the oxygen and nitrogen go? Were they blasted away by radiation? Did some unknown chemical sorting process occur deep inside? At this point, those ideas remain speculative, and scientists are careful not to claim more than the data supports. But the fact remains, every standard formation model seems to hit a wall here. And when an object refuses to fit into existing categories, it forces a bigger question. What if this isn't just a rare oddity, but a hint that we're missing an entire chapter of how worlds can form? Step back for a second and consider how rare this really is. Out of nearly 6,000 confirmed exoplanets, only a tiny handful orbit pulsars at all, and almost none resemble a gas giant. Yet PSR J2322-2650b not only survives around 1, it defies every expectation about what such a world should look like. Its host, PSR J2322-2650, is a stellar remnant no bigger than a city, but heavier than the sun, blasting radiation into space with relentless precision. And somehow, wrapped in soot clouds and molecular carbon, this planet endures. What makes this discovery even more remarkable is that it was only possible because of the James Webb Space Telescope. Webb's infrared instruments can isolate faint atmospheric signatures with extraordinary sensitivity, especially in a system where the host star doesn't flood the view with visible light. From its position about 1 million miles from Earth, shielded by its massive sunshade, Webb can cool its instruments enough to detect subtle chemical fingerprints that ground-based telescopes would never see. But the deeper implication isn't just about one strange planet, it's about what else might be hiding in plain sight. If a carbon-dominated, diamond-forming world can orbit a dead star and escape detection until now, how many other impossible systems are waiting to rewrite the rulebook? In the end, PSR J2322-2650b is a puzzle that refuses to be solved, at least for now. Its bizarre carbon-rich atmosphere, extreme temperatures, and distorted orbit challenge everything scientists thought they knew about planets and their formation. And yet, that uncertainty is part of what makes it so thrilling. Every new observation from the James Webb Space Telescope peels back another layer of mystery, reminding us that the universe is far stranger than any theory or expectation. For researchers, it's a chance to chase questions with no easy answers, to probe chemistry and physics in ways that were once unimaginable. And for the rest of us, it's a reminder that somewhere out there, worlds exist that don't just stretch the imagination, they shatter it. One has to wonder, if a planet like this can exist just 1 million miles from a dead star, what other secrets are lurking in the cosmos, waiting for us to look closer?